Hey everybody, welcome back to chemistry, and we're continuing on through chapter 5, which is the chapter on stoichiometry. And so I want to now go over a problem called a titration problem that involves stoichiometry. And so this is a little bit trickier problem to do, but before I do some problems on the glass board, what I would like to do first is sort of to explain to you what a titration experiment is. And so what I'm going to do is I'm going to go over here to the computer and talk a little bit about what a titration experiment is. The goal of a titration experiment is to determine the concentration of some kind of solution. And so the way you figure out its concentration is by adding to it another solution of known concentration. And then what you can do is follow a particular parameter, and then you'll get some information that can be used in a calculation that allows you to figure out the concentration of the first solution that you're trying to find. So a typical titration experiment, which is done in a lab, and the one I'm going to sort of go over here is something called an acid-base titration. So let me give you a sense of how this is done. So let's say that you have a solution of hydrochloric acid. And so you might remember the formula of hydrochloric acid is HCl. And let's say that you do not know what the concentration of the HCl is. And so what you're going to do is you're going to do a titration experiment to figure out what the concentration of the HCl is. So here we have here in this picture a flask of HCl. The HCl is an unknown concentration, so I'm going to write capital M here for molarity because we do not know its concentration, but we do know the volume of HCl we have. And so maybe, for example, I have 50.00 milliliters of HCl in this flask. So now, how would I go about finding out the concentration of this HCl? Well, this is what you do. You put the flask of the 50 milliliters of HCl onto an apparatus, and so the apparatus includes a stand. And so if you look carefully here in this picture, you can sort of see the flask here with the 50 milliliters of HCl. Now, the titration experiment is done as follows. What you're going to do is add a molecule that will react with the HCl. And so the molecule we're going to add is sodium hydroxide, which is a base. So what we're doing is we're adding a base to the HCl acid, and so we're carrying out a neutralization reaction. So the way you add the base to the HCl is you try to do it very slowly by adding a few drops at a time. And so the glassware you do that with is, I'm drawing a circle around it here, this long skinny tube is called a burette. And so a burette is a piece of glassware that allows you to add drops of a solution into the flask, for example. And also it gives you accurate readings for volumes that you're adding. So imagine what's going on. So first off, you have acid in the flask, and you haven't started your titration experiment yet. And so you have acid, and so you have HCl in here, and all the HCl molecules dissociate into hydronium ions, which is H3O plus, and chloride ions. I'm only indicating the hydronium ions there, but you should know that there are chloride ions in there. Now, what you're going to do is you're going to add base. And so what will happen is as you add the base, which is the NaOH, the base, when it goes into the liquid solution, will dissociate into sodium ions, the Na+, and hydroxide ions. Now, the goal of a titration reaction is add exactly the correct number of moles of hydroxide ions from the base to match the moles of the hydronium ions of the acid. And so the question is, well, how do you determine that? Well, we do a trick with that. And so what we do is before we start the experiment, we add a colored dye called phenolphthaleins, which I'm just abbreviating here, capital P. We add phenolphthalein into the solution. So the neat thing about the phenolphthalein is when the phenolphthalein is in a solution that is almost all acid, in other words, it's almost all hydronium, then the phenolphthalein remains clear. However, when you've added enough base such that you have the moles of the hydroxide is going to be equal to the moles of hydronium from the acid, then the phenolphthalein changes color. So when the phenolphthalein changes color, as you can sort of see in this picture here, again, that indicates that you have exactly the same number of moles of hydroxide you added from the base as the moles of hydronium in the solution. And so when that happens, you have reached something called the equivalence point, where again you have the moles of hydronium is going to be equal to the moles of hydroxide. And so at that point, when you've reached the equivalence, when the solution turns a very light shade of purple, you stop the experiment and you note the volume of base that you dispensed into the solution. And so from that information, from the concentration of the base and the volume of base you dispensed, and also knowing the volume of the acid you started with, you can figure out the concentration of acid. And so what I'm going to do now is sort of give you an example of some data that we maybe got from this titration experiment and show you how we can figure out the concentration of acid. So I have a problem here. It says the end point of a titration of a 50 milliliter sample of aqueous HCl, which is what we had in previous slides, was reached by addition of 35.23 milliliters of 0.250 molar NaOH titrant. At this point, the indicator dye turned purple, suggesting that the equivalence point is reached where the moles of hydronium is equal to moles of hydroxide. And so we want to answer two questions. First off, what we want to do is write a balanced equation that describes the reaction we had when we add base to the acid. And two, what we want to do is figure out the molarity of the HCl that we start with. So I'm going to go ahead and do this on the glass board. So let's first talk about what the balanced equation is for this reaction is. And so what you might remember is we started out, we had HCl or acid in the flask. And then what we did is we added base to it. The base was sodium hydroxide. And so when you add the base to the acid, what will happen is you will get a neutralization reaction. And so one of the things you're going to probably have to do is you're going to have to solve this problem correctly is figure out what the products of this neutralization reaction are so that you can correctly balance the equation, because you'll need a correctly balanced equation to solve the problem. So first, let's figure out what the products of this neutralization reaction are. So you might remember that if you have an acid here reacting with a base, you get, in a neutralization reaction, two kinds of molecules. One kind of molecule is a salt, and the other kind of molecule is water. So let's first figure out the kind of salt that we get. So you might remember how you do this. And so here, imagine the sodium ion breaking off the hydroxide and replacing the hydrogen ion. The sodium is binding to the chloride ion. So the salt we get in this case happens to be table salt, which is NaCl. And then how do we get the water? Well, the hydrogen ion from being bound to the chloride here breaks off and replaces the sodium and binds to the hydroxide. And so now we have H2O. So we have water. Now, one thing I want to do is I want to make sure, absolutely sure, that this equation is balanced. And so I think you all know how to do that at this point. And so what we do is for each element, we make sure that we have as many atoms of that element on the reactant side of the equation as we do on the product side of the equation. So if you look at it carefully, I think you'll find that this reaction, as written, is a balanced equation. So what does this tell you? It tells you that 1 mole of HCl will react with 1 mole of NaOH to give you 1 mole of HCl and 1 mole of water. Okay. So this is crucial information that helps us solve the problem. So let's go ahead and go to part 2 of this question. What we're going to do now is try to figure out what the concentration of the original HCl is. So what I need to do is kind of outline a strategy to solve this problem, because it can be sort of difficult from the information given to you to sort of figure out where to start first. So what I do is I look at the problem and I see what we're trying to find. And then the problem, as I read it, says, what is the molarity of the HCl? So in the end, what we're trying to do is we're trying to find the concentration of the HCl. And so the way we do that is by finding a molarity for that. So the question is, where do we start? What information do we start with which will lead us to figure out what the molarity of the HCl is? The basic rule in solving these problems is this. If you're doing an acid-base titration, here, if you're ending up trying to find information about the acid, here's the concentration of the acid, you start with information about the base. So we're going to start the problem using information about the base, and so the base here is NaOH, and so we're actually given some information about the base, and so we're given the concentration of the base, which is molar, and also we're given the volume of base, which is in milliliters. Okay, now you will take this information about the base, and you will have a couple of intermediate steps. You will have to take this information about the base and convert this into moles base. So you have to convert this into moles NaOH. And then what you'll have to do is once you're at moles NaOH, what you'll have to do is use the balanced equation to figure out the moles of the acid, which is HCl here. So we'll figure out the moles of acid. And then the final step is to take the moles of acid and the volume of acid, which you're given to in the problem, to figure out the concentration of acid. Okay, so let's go ahead and try to solve this problem. Okay, so again, we want to find a concentration of this HCl. We start with the opposite. So we start with the base. Let's get the information of the base, which is the concentration of molar and the volume of milliliters, and get this into moles of base, which is sodium hydroxide. So how do we do that? Okay, so in the problem, let me look up what the concentration of the base is. And so here we have 0.250 molar NaOH, which is the base. So just to make this problem a little bit easier, I'm going to write this in a slightly different way. I think you all know at this point that when you see the word molar, molar means moles per liter. So this is like saying 0.250 mole per liter NaOH. So you can say that, but I'm going to go a little further. I can write this in terms of a fraction. If you're dealing with 0.250 molar NaOH, you can say it's 0.250 mole of NaOH over 1 liter NaOH. So you're allowed to do this. So if you have 0.250 mole NaOH over 1 liter NaOH, that is the same as 0.250 molar NaOH. So I want to use this to start with. So when we see that we have 0.250 molar NaOH, what you should write is that we have 0.250 mole of NaOH over 1 liter NaOH. Okay, so that's our starting point. So what's the next step? We have to get this concentration of NaOH to moles of NaOH. So you want to take this concentration of NaOH and then multiply it by something that will get liters of NaOH to cancel out, leaving moles of NaOH. And so that's not so difficult. We are told the volume of NaOH that was dispensed is 35.23 milliliters of NaOH. And so what I'm going to do is I'm going to just, in my mind, convert that to liters. So if you have 35.23 milliliters of NaOH, that is 0.03523 liters of NaOH. So what I'm going to next do is multiply this by 0.03523 liters of NaOH. Now, one thing that you're seeing now, which you may not see so often, is here, what we have here is we have sort of a number here in the numerator without having it in a fraction. In other words, we have only a number in the numerator and we don't have another number in the denominator. That is possible to have in this kind of problem. You can just take this fraction here and multiply this number, and you're allowed to do that when you're doing factor label method. Okay, so let's see where we're at now. And so what you can see is that the liters NaOH cancels out, and so now if we were to do the math, you would have an answer in moles of NaOH. So we're now here. So the next step is to get it into moles of HCl. So to do that, what we do is refer to the balanced equation that tells us that for every 1 mole of HCl that reacts, 1 mole of NaOH will react with it. So I'm going to write times 1 mole of HCl over 1 mole of NaOH. And so you can see now that the moles and OH cancels out, and so now we're at an answer of moles HCl. So the final step is somehow we have to convert here the moles HCl into a concentration. So we have to take this moles HCl and somehow get this into a concentration of HCl, which will be not in moles but in molar. So remember that molar is moles per liter. So the question is, how do we get this moles HCl into an answer where we have moles per liter? So what we need to do is now we use the volume of HCl. So let me show you how you use this. And so in this problem, we started out originally with 50 milliliters of HCl. So let's just convert that to liters. That is 0.0500 liters. So I'm going to take times 1 over 0.0500, I think we need another 0 there, liters. Now, let's talk about why we can do this. So let's think about what happens. What kind of answer would we get? What kind of units would the answer have? Well, the units that the answer would have, you see that moles HCl never canceled out, right? And here in the denominator, liters HCl never canceled out. And so you carry moles per liter into the answer. Now, what is the math? So the math isn't so bad. It's going to be 0.250 times 0.03523. And then it's going to be divided by 0.0500 liters. And so when you work that out and you correct for a correct number of significant figures, your answer will be 0.176. And again, moles in the numerator and liters in the denominator carry through. So the answer is 0.176 molar. Okay, so now let's go ahead and do another problem. Okay, so this problem is a little bit trickier, so let me bring it up on the slide, and so let me describe this problem to you. It says you carry out a titration, but this time you are reacting sulfuric acid, and the formula for sulfuric acid is H2SO4, with a base, which is called potassium hydroxide, which is KOH. Let's say you need to dispense 12.87 milliliters of the 0.500 molar solution of KOH into a certain volume of sulfuric acid to neutralize it. If the concentration of the sulfuric acid is 0.750 molar, what is the volume in milliliters of the sulfuric acid solution? Okay, so this appears to be a titration problem, and it's specifically an acid-base titration problem. And the way I know that is we are trying to find a concentration of acid, here it happens to be H2SO4, by adding to it a base, which is KOH. And so that would be a titration problem. So we kind of solve this problem using the basic strategy that we saw before. Now, when you get a problem like this, it's very important that you need to know the ratio of the moles acid reacting with the moles of base. And so in order to figure that out, you have to start out by writing a balanced equation for this reaction. So to do that, I'm going to go ahead and I'm going to note here we have sulfuric acid, which is our acid, and it's reacting with potassium hydroxide, which is our base, KOH. Now, in order to balance this correctly, what we have to do is predict the products of the reaction and make sure we write the correct formulas for those products. So you can see we have an acid here and a base here. And so when you mix an acid and a base, you have a neutralization reaction. And so you will get a salt and you will get water. Let's first figure out what the formula for the salt is. And so what you have to do is imagine this potassium ion, which is K+, breaking off the hydroxide and replacing the hydrogen ions, and now the potassium is binding the sulfate. So what is the correct formula for potassium sulfate? Is it this? Is it KSO4? Unfortunately, that is not right. And the reason is potassium has a single positive charge, sulfate has a 2- charge. And so in order to balance this formula, you need two potassium ions to balance the 2- charge from the sulfate. So that is correct formula for potassium sulfate. And then you can write out the formula for water. Okay, so far so good. Now, importantly, what you need to do is balance this equation so that you know exactly how many moles of acid will react with the moles of base. So I look at this, and what I can see is, for example, with the element potassium here, we have 2 atoms as a product, 1 atom as a reactant, so I need to put a 2 here. And then I think to complete the balancing equation, you need to put a 2 in front of the water. And so this should be a balanced equation. So importantly, what this says is that for every 1 mole of H2SO4 that reacts, 2 moles of KOH will react with it. Okay, once we have the balanced equation, we can go ahead and solve the problem. So again, let's figure out first, what are we trying to find here? It looks like in this problem, we are trying to find the volume of the sulfuric acid. So we're trying to find the volume of sulfuric acid. So you ask yourself this question, what is our starting point? Well, if you're finishing with acid, the starting point must be the opposite molecule. So if you're finishing with acid, you must start with base. So you're starting out with the information you have for the base. So the base here this time is potassium hydroxide, and it looks like we know a molarity for it, and we have a volume in milliliters for it. And so the basic strategy will be to take this information, find the moles of base, which is KOH, and then the next step, find the moles of H2SO4, and then once you find the moles of H2SO4, you should be able to, using the molarity of H2SO4, find the volume of H2SO4. So let's go ahead and start at the beginning, and let's take this information about potassium hydroxide and figure out how many moles of potassium hydroxide we have. So we have a concentration of potassium hydroxide in this problem. It looks like we have 0.500 molar KOH, and so I think you know at this point that what I can do to indicate that is I have 0.500 mole of KOH over 1 liter of KOH. Now, I think you sort of know at this point that if we want to take this concentration of KOH and get this in the moles, what we're going to need to do is multiply it by the volume of KOH. And so the volume of KOH, in the problem, it looks like we dispense 12.87 milliliters of KOH. Let's just convert that to liters. So it's going to be 0.01287 liters KOH. So as I kind of mentioned before, it is okay if you have a number here just in the numerator without a denominator. That's perfectly fine. You can do that in factor label problems. So you can see that the liters KOH cancels out. Now we're at moles of KOH. Okay, now we're here and we want to get to moles of H2SO4. So here we have to refer to the balanced equation. And you can see that for every 1 mole of H2SO4 that reacts, 2 moles of KOH react with it. So we have to write here times 1 mole H2SO4 over 2 moles of KOH. And now you can see the moles of KOH cancels out, and now you have an answer in moles of H2SO4. But we have to go a little bit further. We're now at moles H2SO4. Now we have to get to volume of H2SO4, and I think they want the volume in milliliters. So how do we do that? Okay, so our goal is to take what we have now, moles H2SO4, and get some kind of answer in volume. And so it may start out to be in liters, but eventually you might want to get this into milliliters. And so I think we can easily do that. So the question is, how do you take this moles here of H2SO4 and get this into the liters? Well, what we need is a proportionality between the moles of H2SO4 and the liters of H2SO4. If you think about that, moles per liter, that proportionality is molar, that is molarity. So molarity really is the proportionality of the moles of H2SO4 for the liters of H2SO4. So let me write out what the molarity of H2SO4 is in this problem. It looks like H2SO4, so I'll write this here. H2SO4 is going to be 0.750 molar. So I'm going to write this one way. So one way you can write this is 0.750 mole H2SO4 over 1 liter H2SO4. Now, if you wanted to, you could write another fraction with this flipped over. So 1 liter H2SO4 over 0.750 mole H2SO4. And so you have to decide, can you use one of these fractions so that moles of H2SO4 cancels out, and then maybe you get an answer in liters H2SO4. So let me go ahead and write that fraction here. So it's going to be times 1 liter H2SO4 over 0.750 mole H2SO4. So we're now at that point now. You can see the moles H2SO4 cancels out, so we have an answer in liters H2SO4. So the final step is you're going to have to take this liters of H2SO4 and get this into milliliters. And so maybe one of the things you might remember is that if you have 1 milliliter, that is a small fraction of a liter. It's going to be 1 times 10 to the negative 3 liters. Anyway, if you do all this math, I think what you'll see is that the liters cancels out here. You'll get an answer in milliliters. And I think if you go ahead and do this math and to correct number of significant figures, you get the answer to be 4.29 milliliters. Okay, thank you for listening. We'll see you next time.